All right, some characteristics of cardinalities is that if we have a set B that is countable, then any subset of B, we'll call it A, is either going to be countable or finite. So if a set is countable, then getting rid of some elements is still going to preserve the characteristics of being countable, or it is going to be finite. All right, so that's the theorem 1.5.7, and we'll dive right into the proof. So the proof goes like this. Let B be a countable set, and A be a subset of B. Well, since B is countable, there is a one-to-one correspondence with the natural numbers and the B. So we have something. So there exists a function f, we'll call it f, that maps the natural number to B with one-to-one correspondence. And one-to-one correspondence just means that the function is bijective. So we have n, 1, 2, 3, 4, 5, 6, 7, 8. And then a function that maps onto B. We'll say, call these B1, B2, B3, B4, B5, B6, B7, and B8. And these are all mapped. All right. Well, we know that A is a subset of B, so let's just pick arbitrary elements from B that is in A. So maybe this. So all the red circles are in A. All right. So the goal is to find a function g that maps the natural number onto A with one-to-one correspondence. That way we will know that A is finite. Oh, and another, we didn't define A, whether it was finite or infinite. We'll just say A is an infinite subset of B. A is an infinite subset of B. If A was a finite subset, then it would be much more easier to show. So we'll consider the case where A is the infinite subset of B. All right. So what we're going to do is let n1 equal to the minimum of n and a natural number such that f of n is in B. Sorry, this should be A. All right. So let n1 be the minimum of the natural numbers such that f of n is in A. So in this case, what is n1? Well, n1 is equal to 1 because that's our first occurrence, the smallest of the natural numbers, where f of n, which is b1, is going to be in A. And recall that the circled part, the red circles, are the elements of A. What about n2? We'll define n2 be the minimum, again, minimum of the natural numbers, such that fn is in A. However, there's another restriction with n2 being greater than n1. All right, so in this case, what is n2? n2 is going to be simply the second occurrence, which is equal to 4. So n1 is going to be 1, n2 is going to be 4. What about n3? If we do the same thing, n3 is going to be 5, and 4 is going to be 7. All right, so that's n2, n3, and then n4. So define g1 to be f of n1, and g2 to be f of n2, and g3 to be f of n3, and so on. So then, if we continue doing this, we just found a one-to-one correspondence between the natural number and our subset A, the infinite subset of B. Hence, A is countable. So this may seem a little bit confusing, but basically what we're doing is that when we have an infinite subset of B, which are these red circles, and it will go on for on and over, we are just mapping the ones that are in A. So we're going to be just ignoring these parts. And since it is infinite subset, it will have a one-to-one correspondence with the natural numbers. So so we define the function g that does that. And we see that g has a one-to-one correspondence with the natural numbers and the set A. Hence, A is countable. And that's the end of the proof. We know that any subset of a countable set is either going to be finite or countable.